Hello everyone, this is Xuyang Wu from Digital Futures. Today I will introduce our work, Accelerating Asynchronous Learning by Delayed Adaptive Step Service. I will first introduce synchronous and asynchronous distributed learning. Distributed learning uses multiple processors to solve large-scale machine learning problems. One typical architecture is the master worker architecture, where the workers compute information and the master aggregates information from workers to update the model. Two typical update ways in distributed learning are synchronous and asynchronous. In synchronous update, only if all the workers finish their computation and communication, the master will update the model and go to the next iteration. One example is gradient descent, where each worker I compute the gradient of fi based on the current model xk, and the master aggregates all the gradients to update the model. This is usually inefficient because the update speed is determined by the slowest worker. To avoid this issue, one can choose to update asynchronously, which means that once some workers finish their computation and communication, the master will update the model and go to the next iteration. This usually causes delay. One example is IAG, which is the asynchronous version of gradient descent. In IAG, when some workers finish the computation of the gradient, the master will update the model. And for workers that didn't return their gradients, the master will just use the old gradients. This is usually efficient compared to synchronous update. Now we'll give our motivation and the solution. We focus on asynchronous learning with non-diminishing step sizes. In existing works, the step size usually rely on an upper bound tau of all the delays. However, this tau is usually unknown. This will lead to the difficulty in the implementation. Another issue is that this tau is usually large. This will lead to small step size and slow convergence. Our solution is that we believe the step sizes should rely on actual delays rather than the upper bound, because the accuracy of the delayed information is determined by the actual delays. Based on this idea, we derive delayed adaptive step sizes for two asynchronous methods and show its advantage over the fixed step size by both theory and numerical experiments. That's all, and thank you for listening.